MATLAB. So at the campus in the wireless LAN, you should be able to use MATLAB. But don't ask me now how to set up the license server. I know that the license is checked over the internet, the license server in the computer center. So this should work here at campus. Because I know typically I have problems. For example, if I go to Kazan, I cannot access the license server here. So my MATLAB book will not work inside the university. This is also why I typically recommend Octave. It's pretty much the same and it's available for. Worry about licenses at all. Let me write better answer next time. MATLAB running. Yes. Okay, we'll double check. Point of view, this is not really smart. So the students, in order to get some benefit later on when the students enter. Some audio problem. Okay, I should speak more. With the next question about research work. This question is, of course, pretty general. So we basically encourage the students to work scientifically within the second and third semester by working on this student research projects. So this is very interesting and also a good practice and experience if you are looking for jobs in research and development later. So then you already work on typical tasks that are quite close to what the researchers do actually, because these research topics for your student projects, of course, are proposed by researchers in the labs. And so those are like subtopics of the research that they are doing, where this is a small and not difficult problem, we can have a student working on this. But there you are already at the level of research that is currently going on. So I think there we will also have some introductions of topics where you get topics presented, brief comments, what the topics are about. Then you can select in which lab to work. For example, if you like the high frequency stuff with Professor Hein, many students go there. Do you like the higher layer stuff with Professor Seitz on the product issues or physical layer things? You can decide then which way to go. Later on, maybe the question is direct this way. At least I know it from our lab, the Communication Research Lab, had some CSP students going for a PhD in our, so typically the best ones. No? So in each group we have like 2, 3 to the 1.0, 100%, like every, those are the ones who are really excellent to have them in a PhD program. Some more hint. San, they have the license at the university. They are asking if it will work in Germany. So of course, if the KAI license will work in Germany, you need to ask your computer experts at KAI. So this one, but I will check. for all students if it is possible to use the MATLAB license here at the campus. Okay, so I think started. Okay, so then the official welcome to everybody. Welcome to our next lecture. Today we want to talk about the decoding rule, so how to decode received code words in the best way, where we know at each position a transmission error could occur. So what to do with the received code words? So this is the question that we would like to answer today. But before we do so, we briefly repeat what we did last time. We started by looking at the quite general diagram of what we would like to do. Let me use the mouse pointer again to show you. Okay, so we have this channel coder, which adds some redundancy, which will make it possible to detect or to correct errors. How this will be done, we will see later. And we also noticed that there's a price we have to pay for this. In this example, you see, we would need like 3 times the bandwidth. There was the question of a student, why 3 times the bandwidth? This is just like from signals and system theory. If you have random signals looking like this, and we ask for the spectrum, the power spectral density, we could, for example, determine the autocorrelation functions and calculate the Fourier transform of the autocorrelation function to get the power spectral density. You could also use algorithms to estimate the power spectral density directly from the signal. This would be something like the periodogram estimation, but those are things typically done in signal and system theory. This was more for the principle. If we make the bits smaller in time, the bandwidth increases. So the price we have to pay is the increased bandwidth. Okay, and then we talked about some properties of codes. We had the systematic codes where the information bits U are directly a part of the encoded word A. You see, it just begins with these 2 information bits. Systematic code, if it is done like this helps us in the decoding algorithms. We can have linear codes, so meaning any linear combination of any code words will be again a valid code word. So we just briefly verified our set of code words, gamma here, if this forms a set of linear code words. So this means if I pick any combination of code words, the modulo 2 sum without carry of these code words, the result will be a new valid code word, meaning a member of the set of code words. Then we had an important measure for the performance of these codes, as we will see, this so-called minimum Hamming distance. So this tells us how different the 2 most similar code words are in a set of code words. So set of code words, we compare any combination of code words and see in how many bits are these 2 code words different. So for example here, the Hamming distance between the code words 0, 0, 0 and 0, 1, 1 is 2. These 2 code words are different in 2 positions. And of course, a large Hamming distance will help us because this means the code words are more different. More different means they are easier to distinguish. Or a single error will still make it possible to distinguish between these 2 code words. But we will see the influence of this minimum Hamming distance on the performance of our code. We'll see this today. And we also have some specialty for the linear codes. For the linear codes, we can find this minimum Hamming distance a bit more easy. So this means we don't have to compare each combination of code words. We just need to look which code word is most similar to the all zero code word. Because we know for any set of linear code words, the all zero code word needs to be a member. Because the most simple linear combination would be 0 times one of the code words. So the all zero code word will always be a member for a linear code. And the task to find the minimum Hamming distance simplifies then to the task to find the code word with the lowest number of ones, because this will be most similar to the all zero. So we will also see this when we talk about a practical example. Yes. Yes, yes. Yes, exactly. Let me repeat the question for the Russian students. So one student here asked, if you have an increased Hamming distance, of course, it's easier to distinguish the code words, but the drawback is that we need more bandwidth. And exactly this is correct. So just always think about the most simple examples. We had the 3 times repetition code. We have the 0, 0, 0 code word. We have the 1, 1, 1 code word, different in 3 positions. Minimum Hamming distance is 3. But you also know we need 3 times the bandwidth. So now you could say, let's use a 5 times repetition code to be even more safe. Minimum Hamming distance would be 5, because you could also correct 2 errors then in case you detect some errors. But the price would be you need 5 times the bandwidth. So your observation is correct. If we have codes with higher minimum Hamming distance, typically they also need more bandwidth. Need to invest more redundancy. It's very good. Okay. So let us start today by talking about the coding. And there I want to start with a block diagram again to define some variables that will appear later on. So we start with the information bits, vector containing the information bits U. Those enter our channel coder. Let's use again a simple one. Let's think this kind of parity check code where we just append a 0 bit if we have an even number of ones. So the encoded word, we call it A. We introduce this, whereas this is always member of gamma, where gamma is the set of our codes. Then we enter, starting with a simple example, enter a discrete channel. This could be, for example, this from my binary symmetric erasure channel, PE1 minus PE discrete channel. So this is just an example. and the output will be our observations, y. And notice on this channel now, each of the bits could be corrupted by an error, just if the error probability PE hits the bit. So let's see, it could be receive 0. Would need a decoder, which in the best case would correct there. We'll see if this would be difficult for such a kind of weak code, but the task in general this decoder starts with the so-called code word estimator. So which code word was most likely transmitted? Estimator. Just for the notation, this basically uses the received values and it comes up with a code word estimate, called this estimator function delta of, and the estimate of the code word should be then a hat. We always denote estimates with this hat symbol. Delta is the estimation function, estimator function. A hat is the code word estimate. So question from Kazan. Gamma is the set of what? So gamma is the set of all possible code words. For example, if we have 2 information bits, as in our example here, we will get 2 to the power of 2 possible code words. So with 2 information bits, we will get 4 valid code words, and they form this set of code words. I try to get a bit more close to the microphone. Okay. So the code word estimator, the output will be the estimated code word, a hat. And then, of course, we just need to do the encoder inverse. So we need to get back the information bits u, so the vector u hat. Encoder inverse. Estimate for most likely transmitted bits. System D. Well, and in our case, let's say if the code would be strong enough, in ideal case, we would get bits that we actually transmitted, and we would get the decoded bits correctly. So ideally. We will see later on that in our example, this coding scheme would actually not be strong enough to. If you think a little bit about it, you will see it right away. Just look at this received sequence. So the code word estimator could say now, this could result from a 0, 0, 0, or it could result from a 1, 1, 0. Both are valid code words, both have the same Hamming distance, both are equally likely. So for this very simple code, it would not be possible. But this is just for illustration, so let's assume it would work. Okay. So then we have a question, which symbol did you use after the discrete channel? This is a Y. Yes, so typically, I'm not sure how Mike Wolf introduces this binary symmetric channel. I typically use capital X as random variable at the input of this channel and capital Y at the output channel. Okay. Let me see how to. Example. To illustrate the decoding rule. Yes. Yes, let me repeat the question. So the question here was if this decoder is just for the channel or the channel and the source. So I'm not sure if I understood it correctly. Of course, you could now introduce another box in our diagram doing the source coding. So this would go in front of the U. So we assume this bits U result already from a source coder. So for example, Huffman encoded source. No? I think you did this with Mike Wolf. Or you could also say MP3 codec or anything, or a video codec, and this bits would go in the channel code. We could draw more boxes around with the source coding. Yes, but of course, the reason why we decode this is that we have a noisy channel. Channel introduces some errors during transmission, and we want to, basically fight these errors. Okay. So let's come to the decoding rule, and therefore we need to make some assumptions first. So notice here that we talk about maximum likelihood decoding. Often abbreviated MLD. Observe any received code word, which code word has been transmitted with the highest likelihood. Find the most probable code word that was transmitted. Start with an assumption. Quite reasonable assumption. We assume that all code words occur with the same probability. Here, same probability. And just to mention this once more, we have k information bits in a code word. For example, 2 in our example. We will have 2 to the power of k. possible code words or valid code words. If you have 2 to the power of k possible code words, the probability that one of them occurs is 1 over 2 to the power of probability is k. We start thinking about the case where we transmit one certain code word and then asking for the probability, what's the probability that this is decoded wrongly? And then we extend this idea by thinking about what happens if we consider all possibly transmitted code words. So we start from the simple going to the more general. So probability for a wrong detection if a certain code word A was transmitted we are asking what's the probability that our decoder function delta of y produces an estimate that is different from what we actually transmitted. So this is the probability we are looking for. So the probability that delta of y is different from A under the condition that A was transmitted. What's the probability that we decode for anything else but A? And maybe also to give you a hint on the notation, so this line basically means under the condition. Probably there you are not different from German students. Typically the German students start to get difficulties when we talk about conditional probabilities, conditional probability density functions, joint probabilities, joint densities. But here, starting simple, asking for the probability that something goes wrong under the condition that we know we transmitted A. Okay. And we can further express this. This is, of course, the sum. Now summing over all possible received sequences y, for which delta of y produces something else. It's different A. Y received under the condition that A was transmitted. You will understand this right away when we come to an example. I agree, this looks a bit difficult with this labeling of the sum. even a bit shorter. This is just for you to get the meaning being different from A. Ability. Save your questions after the example, then it will be a lot more. And give me a hint if I'm going too fast with the next page. So, example. Yes, just for simplicity, we will use again our 3 times repetition code, the 3,1 repetition code. K being 1 info bit with 2 to the power of K valid code words. Probability of occurrence 1/2. This is not really difficult. Let's also write the set of code words, gamma. Example for this one again. So this is the set of code words. We have 2 possible code words. And now I want to illustrate this conditional probability, the probability that our code word estimator produces an estimate different from A under the condition that A was transmitted. Say A being 111 should be transmitted. And now we want to have a look at all received sequences Y, where our code word estimator would produce an estimate different from. So let me arrange this in a table. This is what we transmit. Then we receive something. Receive. Well, we know the errors could appear at any position of this code word. Any bit could be influenced by an error. Just imagine again this binary symmetric erasure channel. In the worst case, all 3 bits go the wrong way and we observe a 0, 0, 0 at the receiver. We will think about the probability for this. It will be quite low, but it could happen. And just think about all combinations here. It's done most easy this way. We can have 8 possible combinations. So again, as errors could occur at any position, we could receive any combination of 3 bits. Decoded, say here. Yeah, now without knowing theoretic decoding rule, just from our common engineering sense, let's think about the decoding. Of course, if we see 000 at the receiver, what would you say if you observe a 000 at the receiver? Imagine again the example where you write 3 times what I write here at the board, and you would make 3 times the same error. So what would happen if you look at this at home? You would say, I wrote 3 times the same, this must be correct. So you would decode for 000. Obviously, that's correct. The same if you observe 001, you would see I have more zeros than ones. Probably 0 is correct. You would also decode this one for 000. Same with this one. Then we have the first one here with containing 2 ones. You would say, I observed 2 ones. Well, probably a 111 was transmitted. So here the decoder would decode it correctly. Again, one more with 2 zeros, coded for 000, and some more where our decoding would work. So notice if too many errors occur, our decoder will fail, obviously. And now just the question is, what's the probability that our decoder fails? And actually, to now come up with probabilities, we should define the channel model that using G. Here as side note, binary symmetric channel with PE minus PE 0. See, we can additional probability P, the probability to receive a 000 under the condition that 111 was transmitted. Yeah, well, going 3 times the way of a failure here in the binary symmetric channel. This will happen with probability PE. Next one also, PE. Of course, we assume subsequent bits are statistically independent, so the probabilities just get multiplied, set of bits. Then we can ask the same question for the next one. So what's the probability to receive a 001 of 111 was transmitted? Well, in this case, we have 2 times the error case, 1 times the correct transmission. This will be PE, PE, screen here, that's the good case, 1 minus PE. And so on. Let's come back to our sum, to our probability that we were looking for. So the probability, using again the shorthand notation for this on top, y given A, delta being different A under the condition A was transmitted is now basically the sum over all the probabilities that yield a wrong estimate here. Let's write this as a sum. Sum over all possible received sequences Y for which delta of produces an estimate being different from A. Let me use some color here. These are the red cases. Considering all Y's for which we get a coding mistake, and we need to think about the probability that this actually happens, and this will be the probability for Y under the condition so write this on top of this guy here, that's this probability, this conditional probability. In our case, we could actually write this down. We would get a PE to the power of 3 from this guy plus square is 1 minus PE plus and so on. Yes. Yes, yes. So here's the question. Yeah. Yes, so if I understood it correctly, here's the question: what to do with the probability of for the code words to appear this 1 over 2 to the power of k. So far we didn't need this because so far we only considered one specific code word that was transmitted. In our case, the 111 code word. So we will need the probability for the code words in the next step if we ask what's in general the probability that something goes wrong. And then we can have the case, what's the probability that we receive something being different from 111 if we transmit 111? And what's the probability that something goes wrong if we transmit 000 and we decode something different from 000? So as soon as we consider all possibly transmitted code words, we will need the probability of occurrence. Here's the next question. Can you please explain us the decoding part? Yes. So let's come back to this decoding part where we see here the possibly received sequences and the transmitted code word. So we know we transmit a 111. So during the transmission over this page here, over this binary symmetric channel, any of these 3 transmitted bits, 111, could be corrupted by an error. So in the worst case, all 3 bits would end up at the wrong place here at the channel output. We move in of 111. Worst case, we would observe a 000 at the receiver. The probability for this to happen is very little. Just imagine a PE maybe of 10 to the power of -3, little bit error probability. then this product would be already 10 to the power of -9. So 1 out of a billion bits would be wrong in this case. Or probability 1 over a billion, this would happen. And now the question was for the decoding part. Well, simply from our engineering understanding, of course, it makes sense to make like a majority decision at the receiver. If I use this 3 times repetition code, of course, it makes sense to decide in favor of the bit value that appears more often. If I observe a 0, 1, 1, I would decide I see more ones than zeros, probably a 1, 1, 1 was transmitted. So very simple decoding rule, which we will actually also see in the formulas later on. But so far, for this example, it's just from general understanding. So, okay. Now we want to extend this idea, as we already said, to all possibly transmitted code words. Put this on the next page. Extension. All possibly transmitted code words. Now we are asking the general question, what's the probability that our code word estimator produces something different from. Now notice we don't have the condition now that we only transmit one specific code word. Now we need to consider all possible code words A. That's the difference now. And we do this basically by summing over all possible transmitted code words, so over A and gamma, and there we need the probability of occurrence for a certain code word A. P, A, well, and here we again have this P of delta of Y being different. Under the condition, so I have this one here, that A was transmitted. Let's explain this a bit more. I know the equations always look a bit difficult, but that's why we always write a couple of words to this. Probability that A is transmitted. And that's the probability to make a decoding error if A is transmitted. And with this sum, we basically now loop over all possibly transmitted code words. And this, of course, means we need the average. We need to weight each of these probabilities with the probability of occurrence for the code. Here we have an interesting question from Russia. Excellent. If you have transmitted length 4, so the The question is, what happens if we use a 4 times repetition code? And of course, you see then things will be difficult. So what do you do if you receive a 0011? The decoder could not decide with equal probability. It would be either the 000 or so a 4 times repetition code would actually not be a really smart idea because you have the case where you could not decide safely. Okay. So that's this probability for any coding error. And I used a bit here. We have some space. That's good here. Sum of A, gamma, A. And we evaluated this probability here at the back, just 1 page before. It's now summing over all possible received words that an estimate different from. Here we had the sum again over all s, for which y, which delta of y is different from p of y given a. Is where we get decoding error. And again, if you have difficulties understanding these equations, always imagine this very simple example with the repetition code. It's very easy to see all these elements in the sum. You can easily understand it this way. Now we know the probability for a code word to occur. This was 2 to the power of minus k, case 1/2. So this simplifies a bit further. So this will be sum over all possibly transmitted code words. The probability, there now our assumption is into the equation 2 to the power of k, and we sum over all possibly received sequences for which our code word estimator makes a mistake. Maybe now this next step is also a bit tricky to understand. I combine the sums. So you see this 2 to the power of minus k. In our case, it's just 1/2 as a constant. So I can move it in front of the sum. So then I have 2 sums, 1 over all possibly transmitted code words, 1 over all received code words. So I will combine this sum just by using this notation here, sum over a of gamma and over all y's, for which delta of y is different from p of y given a. And that's the probability for any decoding error. So right, it's slightly different. Of being different. A. I can always express the probability for an error as 1 minus the probability for correct transmission. Just flip it around a bit. 1 minus the power of minus k, summing over all A gamma, for which delta of y is the same as A. So this would be the probability for a correct detection. A. Some color here. Correct detection. What's the difference here? Here we have and to introduce one, we call this also PW, just the probability. Probability that word, one code word, is and we actually want to minimize PW minimize so you see PW is 1 minus the sum of these probabilities. So the larger these conditional probabilities will be, the smaller will be PW. This means we need to maximize This brings us to the decoding rule to find a code word estimate that maximizes this conditional probability. Express it this way. P given A hat. So A hat will be our estimate at the end. That is larger or equal than any other P of Y given, yeah, let's call it B. For all possible B being element. We'll also get back to our example to see now how we can understand this decoding procedure. So for example, assume we receive a being 0, 0, 1. We need to find A hat such that this conditional probability is larger than for any other members of this set of code. So this means we need to compare ones with A 0, 0, A being, so the two possible code words that could have occurred. Let's say B goes B, then it suits better that we wrote. And we get B, the conditional probability of Y given B So if we transmit 0, 0, 0, the probability to observe a 0, 0, 1 would be times the correct transmission, P squared, times wrong, 1 times the wrong transmission. Whereas here, given B, 1 times the correct transmission, 1 minus PE times PE squared. And you see here this PE square. So the second probability will be a lot smaller as the first one. This one is sure. This means we will decide for A hat. This one. Decide. Probably 0, 0, 0 was transmitted. If 0, 0, 1 is observed. This maximizes our conditional distance. And if you think a little bit further about this, you will see that we can easily come back here to the Hamming distance. So look at the first code word B000. It's different in one position with the received one. So here we have a B. If it was the second one, 111, we have a Hamming distance D being 2. And you see that this number of different bits directly scales this probability. So if we had a D3, we would get here PE to the power of 3. It would be even smaller. So the more similar these two are, the higher will be the probability. This is from our engineering understanding. Of course, this completely makes sense, but now we actually showed that this is also true if you think about it theoretically by thinking about this conditional probability. Let's also write this in a sentence. P I given A is maximized if choose A hat such that it has smallest distance to 1 as compared to the code words B element. So express now this decoding rule in terms of Hamming distance. So we need to get our code word estimate such that the Hamming distance between Y and A hat is smaller, equal than the Hamming distance between Y and B for all B element. So we need to decide in favor of distance. Maybe expressed in general, decide for the valid code word which is most similar to our received sequence. Most similar in the sense of the Hamming distance, meaning which has the lowest number of different bits. I did also a sentence here, decide for the code word being most similar to the received sequence. In sense of Hamming distance. So we basically showed that our first approach, of course, makes sense, deciding for the most similar one that we receive. Seen this by looking at these conditional probabilities and also using the Hamming distance to explain this, or to even more simple. Okay. So of course, this is true if we just consider this binary transmission, for example, using this binary symmetric channel. It gets a bit more difficult if we consider an additive white Gaussian noise channel, where we can have any real valued received values. Then of course, there's no point of using Hamming distances anymore. If my received values can be 1.3 or minus 0.5, so there's no point of having a Hamming distance. There we use so-called Euclidean distance. So of course we could also measure how similar is this received sequence to what I actually transmitted. Just the measure is then not the Hamming distance, but the Euclidean distance. We also write this very briefly. Later on, we also have examples for this one with some numbers. Or arbitrary received values e.g. from an additive white Gaussian noise channel. We use Euclidean distance. Instead of the Hamming distance. We could also derive this in a similar way, just this conditional probabilities will be conditional probability density functions, but the result will be the same. We would again see we need to maximize this conditional probability density function in this case, and we can do this by minimizing the Euclidean distance. So here, let's define it this way. So we are looking for the code word estimate A hat that has the smallest Euclidean distance as compared to all other possible code words B, B, distance. And here, let me write the note for you example C later. Strange, sometimes it's not writing this thing. Example C. So we basically measure then distance between two vectors. Space. Yes. Very good. Here wants to notice a mistake in writing. It's here not a comma, it's not a joint distance or something. Wait. It's here actually The Hamming distance is no conditional distance. It's the distance just between these two guys. And here the same, of course. It's no conditional distances, of course. It's a comma here. Distance between these two guys. Yes. Do you have some more questions? We will talk a bit more about the measure that we will use to evaluate whether such a coding scheme is working well, so good. We will need to have a look at this code word error probability, but of course at the end we are also interested in the bit error probability. Those are two measures which we need start this one. So code word error probability. Bit error. And it's actually not so difficult, but I had kind of a hard time to come up with some nice lecture slides about this. And it's still not perfect, but you will see it's not so difficult to understand. Okay. So example. Let's assume we have information words. Let's use one bit here. Considering again n, block code. So we have being 4 info bits here. And assume we transmit like this. Just here. Assume blocks are transmitted. So we transmit 10 times 4 information bits. So overall, we transmit 40 information bits. It's 4 it's to be transmitted. And we encode those ones. maybe assume we just append a parity check bit. Okay, so this is the code A containing our example here n 5 bits. So this means overall, 10 times 5, 50 bits are transmitted. Times n 5, 50 bits. Transmitted. Actually, on the first step, we could also have written 40 bits to be encoded. No? But actually, the goal is at the end to transmit this 40 information bits. This is still fine. Then we have the transmission. And we receive some, this is here y. Are received as y. Just what could happen. Because now we could get this. So we would also have the d. Stage. And at the end, of course, a U hat. Those are actually the variables that occur now in ask for different probabilities where things could go wrong. We could ask for the probability, for example, that what we denote here as A hat is different from, let's take, of course, this in front of, it's just the A, not the A. This is what we transmit. We could ask for the probability that A hat is different from A. We could ask for the probability that Y is different from. We could ask for the probability that U hat is different from U. See, we can ask several questions here now. And I want to start with this one. Example here. So, word error probability. Probability serve sequence being different. A. Here. So just imagine if one bit would be wrong now. Then for transmission, with 5 transmitted bits, 1 will be wrong. So error probability 1/5. Explain this in more detail. G. 1 bit. We transmit 5 times 10, being 50 bits. PB, the bit error probability would be 1/5. One code word wrong out of 10. W. So now imagine other cases. For example, it could be that I transmit these 10 code words and we have 5 bit errors occurring and all in the same code word. So we could also have a case with 5 bits being wrong, so probability 5/50, and the code word error probability still being 1/10 because all the errors are in one code word. So this is actually why we get this relationship now. We have the bit error probability, B, so in the worst case where all bit errors would occur in one code word, we would get here PB 5/50, 1/10, so being the same as PW. So this will be the upper bound. Whereas in the more usual case, where we have only one bit error inside one code word, you see we have the relationship PW will be 1/5 or 1/n times PW. So this is the more practical case, one error in a code. And here would be the case, all bits wrong in a code word. Sorry? I didn't understand. Could you repeat? Was the question related to this? Okay. So there it depends again a little bit where we measure bit error probability. Because we could also define the word error probability for our decoded use, for example. And we would calculate, of course, with the 4 information bits, code word length of 4, and see what's the probability that we get wrong bits in U hat. It's a little bit a different question. So this is why I made this quite detailed, this drawing of what I described now is basically what is going on before we actually start the decoding. Yes. Maybe let's make this clear. Or decoding. This is also what I meant with, if you look at the lecture slides, I'm also not really so happy with this representation I've chosen there. But to make it more precise, you will need to distinguish between all these different bit error and word error probabilities. We would need a lot of variables distinguished, but at the end, we are actually interested in the bit error probability after the decoding. And we will speak about this next time in a bit more detail, because there we can also come up with a good approximation for this. And then we will also see basically how theory simulation actually match. Maybe I can show you this. It's a good slide. So this is basically a typical slide. I think students from Russia should also see it because I shared the whole screen again, where I use this approximation that we will figure out. So this theoretical result for the probabilities and comparing those to a simulation. Simulation is the dashed line here. Theory is the solid line. And you see we can come up with quite good estimates for the bit error probability and the word error probability. So displayed both. But we will talk about this in more detail next time, next lecture. So we complete this, we can also solve some tasks related to this. Do you have questions related to this?
Hello?
Yes, we can hear you.
Yeah, can you please go to the previous page?
Yes.
Over there, you calculated for d equal to 1 and d equal to 2 the probabilities. Can you please explain why for the first one it's 1 minus p whole square into p, and for the second one it's I just got confused. I thought it would be the other way around. Maybe I miscalculated.
Okay, so yeah, you heard the question. So the question here was why we use 1 minus PE square here. So let me start with the question we were asking there. We observe a 0, 0, 1 at the receiver. Because at the receiver, we don't know what was transmitted. We just have our observation. And from this observation, we need to decide what was most likely transmitted. What could have been transmitted is one of our 2 valid code words. So either 0, 0, 0 could have been transmitted, or 1, 1, 1 could have been transmitted. And the question is, which one was more likely transmitted? And if, for example, a 0, 0, 0 was transmitted, and we consider a binary symmetric channel with erasure probability PE, then the probability that 0, 0, 0 was transmitted, and we observe a 0, 0, 1 is exactly this probability here. So basically the probability of having 2 correct transmissions over the binary symmetric channel, 1 minus PE times 1 minus PE, and one wrong transmission, so this last bit here, instead of the 0 we transmitted, we observe a 1. This will happen with probability PE. So the probability that 0, 0, 0 was transmitted, if we observe 0, 0, 1, is exactly this one. And we need to compare this probability to the second possible case. It could also have been that 1, 1, 1 was transmitted. And we ask again for the probability that this happened. If 1, 1, 1 was transmitted, we need to have had 2 transmission errors with probability PE, so PE times PE, and 1 correct transmission, the last bit, with probability 1 minus PE. So the probability that 1, 1, 1 was transmitted, if we observe 0, 0, 1, is this 1 minus PE times PE square. And of course, we decide for the one with the larger probability, more likely to have happened. And this is the first case. So if we observe 0, 0, 1, most likely 0, 0, 0 was transmitted. Does this answer your question? So the probability.
Yes, thank you, Professor. Actually, I miscalculated a bit. No, thank you.
The probabilities result from our channel model, binary symmetric channel. Other channel model, other probabilities. But just for simplicity, we use the most simple channel model here. Okay, do you have further questions?
Sir, I have a question. Is my voice audible, sir?
Sorry, you were hard to understand.
Sir, is my voice audible?
I think I don't understand you. Can you type it quickly in the chat window?
Okay.
Some more research in communication engineering to make these tools work better. The random channels, do we calculate the Euclidean distance on? Okay. So here's again one question related to the Euclidean distance. Let me briefly comment on this. We will have a more extensive example about the Euclidean distance, but just to give you an idea. So what we considered now, so erase this and make it not so nice. For example, we transmit this and we receive, for example, this, and we ask for. And now if you talk about Euclidean distance, when this plays a role, you could think about an example where you do a simple bipolar binary modulation scheme, for example, as you know it from Mike Wolf's lecture. We could do a mapping here to +1, +1, +1. Do a mapping to -1, -1, -1. Assume we transmit the first one and we receive a 0.9, 1.1, 0.8. And then we would calculate Euclidean distances to +1, +1, +1, -1, +1, -1. Euclidean distance. And if you would calculate the Euclidean distance, you would see the Euclidean distance between this received vector and +1, +1, +1 is smaller as the Euclidean distance between this received value and the -1, -1, -1. See here. Smaller Euclidean distance. decide for +1, +1, +1, decode 0, 0, 0. So this is just the difference between the Euclidean distance and the Hamilton distance. And now we have the question, how did we obtain 0.9? For example, we obtain this if we have here an additive white Gaussian noise channel with a channel model looking like this. Here our A vector, we have a noise vector, and we have a received vector. Now basically any values could appear at the receiver, but don't worry, we will have a more detailed example. We could also define the noise vector in this example. This would be a -0.1 in order to make it match. 0.1, 0. So just the arbitrary example with some noise numbers imagined. But we will get back to this in more detail and calculate the Euclidean distances. Don't worry. But I think this should answer your questions. Questions. Okay, I think then we are done for today. Thank you for your attention, and we will meet again on Thursday for another lecture seminar. Okay, so then take care and goodbye.
Goodbye.
Goodbye.